Welcome back to the PLC Professor's Workshop and Development Lab. This next project, M22, that's part 2 of the CCW with Micro800 course. You could call it semester 2 if you want. This particular lab project is all about working with comparison instructions. Not the most exciting lab project, but the comparison instructions are extremely important for a lot of applications. So let's start looking at them. Looking at this logic, are any of the inputs on? Well, you don't have to look far to see. You could even look over here on your simulator and see that there are no inputs on, but more importantly, when you look in the logic here, you see input 0 and input 1, and neither one of them is on. Now in the lab project manual, we use the actual hardware memory locations. Here we're using the buffered I/O. IN00 is the buffered _IO_EM for embedded, _DI for digital input, _00, and the same for IN01 is the buffered value from the screw terminal hooked to input 1 on your controller. Which, if any, outputs are on? Well, output 0 is on, and you can see that as well on the simulator. Why? It's on because you have a true coming out of this instruction, and you have a true going into it coming out of this instruction. And actually this instruction is not true or false. This is an any data type 2 double integer. So we're taking the elapsed time from this timer data type up here called number generator, and we are converting it from a time data type to a double integer. And then we're using the double integer in this comparison instruction that is true if 0 is less than 1, if the number is less than the test value, if input 1 is less than input 2. Below here we have just the opposite. We have a greater than. So if the number, which is 0, is greater than 3000, then this would be true. And you can see it's not true because you have a blue rung state out. Now the comparison instructions in 500 and 5000 were more difficult to use because you had to read them. In other words, you had to look, first of all, to see what kind of comparison it was. Then you had to look at the test values, or the source A and source B, and you had to decide whether or not it was true. There was no indication on the screen whatsoever whether it was true or false. Now here we know that this less than is true because you have a red state out. So the rung state out of this instruction is true. And of course it wouldn't be true unless the rung in state was also true. Otherwise it would be false at this point, even if this were true. Now in this case, this instruction, any to dent, does not have a true false state, period. Notice it's EN out. So whatever the input value is, in this case unconditionally true, is out to the next instruction. So you could ignore this first instruction regarding whether or not this rung is true or false. Now, what is the TON waiting for to begin timing? It's waiting for input 0 to go on. So in the lab manual, it says flip input 0 on and observe. Now, if you were using all virtual, you would just toggle this bit on. Well, you can't do that here because it's buffered from this input. So we will turn on input 0. You see the rung goes true, and after 7 seconds, this is going to time out. In the meantime, this is true for 4 seconds. When this gets up over 3000, you'll see this go true and turns on output 2. So you see output 0 is on for just during the time that this number is 0. Because remember, 0 is less than 1, so this would be true. Well, it's only going to be 0 now for one program scan. So you're really not going to see it actually react. It actually does. Once in a while you might see this turn red. But you'll notice that this turns red as soon as this gets to 3001. It's higher, greater than, turns red, turns that output on. Real simple logic. The whole idea here was to give you the opportunity to observe the less than and the greater than instruction. That's all there is to it. In the next lab, we continued on with our, well, it's the same lab. We continued on with our comparison. As my want is typically to do something different in the lectures than I did in the lab project manual. I mean, they support each other. What we do in our discussion supports what you did in the lab project manual, but we tend to want to take a little bit further so you're getting additional information, additional experience. And what you can see here that I've done is that I have more rungs and more instructions. As a matter of fact, if you scroll down, see I've got quite a few more rungs and things displayed that aren't in the manual. First item is we have a counter, and that allows us to have a value that we can control to use for our comparisons. And then we have some test values, in this case 1 and 3. And we're going to use multiple test values. If you look down through here, you can see that I've got other test values. Here's 3 and 4, where I want to compare these two rungs. I want different test values. Now the values themselves are the same, 3 and 1, but the variables are switched over so we can compare these two rungs with the test values varied. So you see here we have true in, false out, true in, true out. That's because this instruction is true and that one is false. So let's jump back up here. Okay, and let's start with less than and greater than. So it's input 1 is less than input 2. Input 1 is greater than input 2. When you're talking which side of these symbols the variables go on, the I1 or input 1 goes to the left of the symbol and I2 goes to the right when you're reading these. Now remember, I told you before that with anything RS Logics, you can't tell by looking at the instruction whether it's true or false. Here you can, even if the instruction is in the middle of a group of instructions, you can tell by the state out from that instruction whether it's true or false. So you can see here that the state out of this instruction, see it's red. There, this one's blue. So the color of this little line coming out of the instructions tells you whether or not it's true or false. Red true, blue false. Okay, so 0 is less than 1, therefore it's true. 0 is not greater than 3, therefore this is false. And if we increment up our number, let's just go to 1. Now you see they're both false. That's because 1 is not less than 1. And so both of these are false because 1 is not less than 1 and 1 is not greater than 3. So we'll do another n. Now we have 2. These are both false because 2 is not less than 1 and it's not greater than 3. So basically you can see that there are a range of values between these two rungs that the instructions are going to be false. Now let's reset it. We could go all the way up to 7, which we did, so I'll keep going here. Okay, now notice here that this is 3 and this is 3, but 3 is not greater than 3. If I go one more count, now you can see that this is true. This is going to stay false until the count gets back down to 0, which we can get there quickly just by clicking on input 27, and that resets the CV for that counter instruction. See, I have input 27 here. Now you're probably, if you're using a digital field device simulator, you probably only have 6 inputs and 6 outputs that you have wired up to switches and lights. In that case, instead of using IN27, I would just probably create a Boolean variable called reset and put it in there, and then just go toggle it from your mouse. Toggle it on, toggle it back off. Okay, we're back down to 0 now, so let's drop down here to something else. Now this was really the next instruction that we did, less than or equal to. And you could easily compare this one with this one. Okay, they're both true right now, right? These two instructions are true, but this one is false. But remember, we're doing an OR, not an AND. So this value is less than 1. If I go up 1 with a counter, now you can see this one's true and that one's false. So as long as one of these two is true, then we get a true out to the output 2 over here. So if I1, the counter count, is less than 1, which it's false here, or if it's equal to 1, true. Reset, and then move on down here. Less than or equal to, we have the same situation. Less than, 0 is less than 1. If we increase by 1, it's still true because it's equal to, less than or equal to. Now if we go down here, we're going to have to get up above 3 or at 3. So up here when we had 3, okay, this was still false because 3 is not greater than 3. But if we make it an OR equal to, then the combination of these two gives us a true. So what I wanted to show you was that this rung and this rung are equal. This is less than or equal to, this is less than or equal to, but the combination of less than or equal to is combined into one instruction. So you have 4 instructions in play here, less than or equal to, and we can compare these two rungs with this rung. So this rung right here and this rung should always have the same output condition. See, output 2, 3, they're both on. We increment by 1, they're still both on. Increment by 1, now they're both off or false. So that's what we were doing here. I just threw in some rungs of logic that you were going to see a little later on. In other words, we had a section on equal and not equal and adding those in parallel with less than or greater than. Now if we slip on down a little lower here, this was some code that was in the earlier part of this lab. I'm going to clear by toggling input 27 so you can see that all 3 of these are false. Okay, and what we did here is we swapped the instructions just to show that it doesn't matter what order they're in, they're always going to be equal. So if you watch these two, both rungs are false. Both rungs are false. Both rungs are false. And they remain that way. Both rungs are false. Now the instructions aren't the same. I mean, this one and this one are the same. See? 4 greater than 3. That's true. 4 greater than 3. That's true. The problem here is that we got a false in. So the rung state, if you got a false in, you're going to get a false out, period. So these are better than RS logics, but they're not perfect. If it were me, I would make a little piece of line right here red if this is true, because I'm looking at this and 4 is greater than 3. If I clear it, okay, 0 is less than 3, that's true. 0 is not greater than 3, that's false. So if I took the less than, 0 is less than 1, but this, you don't see anything about this that marks it as true. That's one thing I don't like about the comparison instructions. These are slightly better in that you got red and blue, but you don't have red and blue throughout. In other words, if you got a false in, you're going to get a false out. It doesn't matter whether this is true or not. So there's still a little visual discrepancy here in my mind's eye, but it's still better than RS Logics. This is the next section, or the next couple changes for equal and not equal. So if we look at rung 11, we have if the count, which is now 0, is greater than 1 and less than 6 and not 4, then turn on output 9. So as we count up, and I want you to pay attention to, in the book it'll say, did adding the not equal with a test value of 4 change the result? Yes. Which values of CV will render the rung true or output 0 in the on state? So as we're looking at output 9 here. Now notice that I have different memory locations, different variables here than I had in the manual. That's because I've got all this code in one big program file, and I have to use different variables, otherwise they would conflict. So let's bump this up 1, and you can see none of these instructions are true. 1 is not greater than 1, nor less than 6, and it is not equal to 4. The problem is you can't tell by looking at this instruction that it's true or false. But basically this says that input 1 is not equal to input 2. Well, we can see 1 is not equal to 4. So this is true, but both of these are false. So we'll count up one more. And now we have all 3 instructions true. So this is a value of 2. So in your manual, you would have I guess you could say, a T next to the 2 and the blank next to 2. That for value of 2, that is true. We go one more to 3. So that means 2 and 3 are both greater than 1, less than 6, and not equal to 4. Go one more, and now we have a count of 4. 4 is greater than 1, it is less than 6, but the not equal to 4 instruction is now false. So the output is off. If we go to 5, now we're back to true again because 5 is greater than 1, less than 6, and it's not equal to 4. If we go one more to 6, now 6 is greater than 1, 6 is not less than 6, although 6 is not equal to 4. Okay, that's that rung of logic. And then this rung of logic down here, and I will toggle 27, input 27 to get rid of the count. If I look at my count down here, I have less than 3 or greater than 6. So right now it's true. 1 is less than 3. 2 is less than 3. But watch. 3 is not less than 3 and it's not greater than 6. So that means for a value of 3, now 4, now 5, the rung is false for 3, 4, and 5. If I go one more to 6, it's still false. One more to 7. Now it's true because 7 is greater than 6. And you can see by changing this less than to less than or equal, or change this to greater than or equal, that you would then include 3 and 6 into the group of values that would make this rung true. Now the whole purpose of doing this, because this is not a practical application, but when you're comparing the comparison instructions, how they behave, this is a good way to do it. Throw in a whole bunch of instructions and then have them all look at the same value to see how they react. Now, if I2 here, or input 2, is 1, 6, and 4, a true comparison, you'd have to make them all the same value. But play with this until you're satisfied that you understand what you see. Also keep in mind that I made this somewhat confusing by having test value 2 being a 1, test value 1 being a 6, test value 3 being a 4, and so forth. I probably would have been ahead of the game to make test value 1 equal to 1, test value 2 equal to 2, and so forth, just to take a little of the confusion out of it. One thing I want to say about this combination of comparison instructions, less than or greater than. And of course, it all has to do with what you have in here for input 2 or I2. I have a 3 and a 6. So this is analogous to a limit instruction. So this rung is going to be true for 0, for 1, for 2, but not for 3, not for 4, not for 5, and not for 6. If I go one more, now it's true again, and it'll be true no matter how high you count from this point. So it's a limit instruction basically that says that this rung is true outside of the limits of 2 and 7, or if you want to include the limits, it's true for 2 and below, 7 and above. So in other words, it's setting limits, and the rung is going to be false in between those two limits. In this case, the limits of 3 and 6. But we're including 3 and 6, 3, 4, 5, 6, because they are less than and greater than, not less than and equal to, or greater than and equal to. If you make them or equal to, now only 4 and 5 are excluded. In other words, the limit is set on 3 and 6, and 4 and 5 are false. The rung would be false. So this is a type of limit combination. Now there's actually a limit instruction that we will get to later. Okay, we have one more piece of logic to look at for M22, the comparison instructions. And of course, this is not exhaustive for all the comparison instructions. We only did the basics. So we've reset to 0. Our count is 0. So we look and we see that the rung is true because the value 1 is less than 0. But 0 is not more than 6, and it's not equal to 4. So that means the rung is true for a value of 0, but not for a value of 1, not for a value of 2, not for a value of 3, not for a value of, well, for a value of 4 it is, and then when we go to 5, you'll see it goes false again. So this rung is true for less than 1, greater than 6, and for a value of 4, right in the middle of the range of values that give you a false out for the rung. So this would be an application where you wanted a bit that's on if some value is less than 1 or greater than 6, or it's equal to 4. You've picked one right in the middle there that you want it to be truth for. Can't imagine what that application is, but I think you get the idea on these instructions. They're kind of hard to look at. And I didn't make it any easier by having variable names like test value 1, 2, 3, 4, 5, 6. I should have made the actual value in the variable to match the name, just to make it simpler. So you get the drift. Reset. If I don't explain where to get the manuals and what they are in the videos, then I get dozens of emails asking where to get the manuals. This RSLogix 500 manual is really the culmination of quite a few years of MicroStarter Lite, MicroStarter, and RSLogix 500. RSLogix 500 will program all SLC 500s and all MicroLogix. MicroStarter and MicroStarter Lite will only program MicroLogix. The starter is not free. It's about $200. Starter Lite is free, but Starter Lite will only program the MicroLogix 1000 and 1100. Then for 5000, RSLogix 5000, Studio 5000, we have 3 volumes, Fundamental Programming, Programming Examples, which is really one manual broken into 2 volumes, and then the Advanced Discussions and Lab Projects. The software for this hardware that this programs, the least expensive license is about $1,000, just under $1,000. And the hardware is also relatively expensive. You can find used compact Logix with some I/O for in the $500 range, but the minimum license is going to be just under $1,000. For Connected Components Workbench with the Micro800, the software is free. So you don't have to buy any hardware. Starting with version 12 of CCW, they included a simulator that works really well. And we really emphasize the simulator in all of our manuals. We also have a separate volume for PanelView 800 and PowerFlex 525. The PanelView 800 projects in this 3rd volume, they are integrated into the actual lab projects in Part 1 and Part 2. So after you do a lab project in Part 1 or Part 2, for the most part, most of the labs, you can then immediately go to the 3rd volume and do a panel view lab that integrates with the project you did in Part 1 and or Part 2. Not all the projects in Part 1 and 2 have PanelView 800 projects that complement them. And then for PowerFlex 525, we have both projects using controllers, and also we show you how to hardwire your PowerFlex 525s with push buttons and lights. For the volumes that you see, the lecture discussions are complete and available for all but the Part 2 of the CCW manual. Most of them are complete and currently going on YouTube free, and we don't have any done yet for the 3rd volume for the PanelView 800 or PowerFlex 525. But keep in mind, you don't need to subscribe to the videos to do the projects in these manuals. The videos are for people that would like a little bit more explanation and tutoring. Have a nice day.